Okay, good morning everyone. Welcome back to our lecture number 4, DC-DC converter. For the first part, 2 weeks ago, I already explained the analysis technique and direct converters, including buck converter and boost converter. So let me just briefly review a little bit the main important point of buck converter and boost converter. So for buck converter, buck mean down. We use it to convert high voltage to lower voltage for DC source. So the most important formulation that you need to remember, this one, the output voltage equal to the duty cycle times this source voltage. So D taken from 0 to 1. So V2 is always less than V1. And for the boost converter, here is the final formulation. You have, I have another one or not? No. So from this formulation, you can see that 1 over 1 minus D is always greater than 1. So for boost converter, you have the voltage at the output always greater than the voltage of the input. Okay. And both converter, for both converter, we can derive this final formulation using the average voltage of a storage element equal to 0, particularly not all storage elements, average voltage of inductor equal to 0. For capacitor, average current equal to 0. So actually we only just use this property for the period steady state. Then we can find a relationship between V2 and V1 for both converters. Okay, and for the process to get to this formulation, to get the expanded form of this average voltage equal to 0, how you get this? You just need to draw the graph of the voltage of the inductor in the case of switching on and in the case of switching off. Then you can find the average value. Finally, you get the relationship between V2 and V1. Okay. So now let's try another example, which is a little bit more complicated, but anyhow you can still use the same approach for the half part, and you need to consider another more method to completely solve this problem. Duplicate. Okay, so let me explain this exercise. So this is also a boost converter, which actually is the real, not the ideal one. This one is happen in the real boost converter. Why I say this? Because as you can see here, we have what happened? Sorry, so I need to figure out what happened with this. Perhaps I used full screen twice. So I need to escape for everything. Okay. Let me try again. Duplicate. Okay. I say this is the real boost converter because in here you can see the internal resistor. So internal resistor always exists, whether in battery or in the circuit of the input part. So this is one of the challenge for boost converter. Actually, internal resistor can affect the behavior of the boost converter that we want. So in here, other than the internal resistor, Other part are just normal boost converter. So how boost converter behave? So you need to control the duty cycle here to switch on and off at the MOSFET. So when you switch on, the energy stored in the inductor, because here you have resistor which is obstacle, so current does not flow this way. When you switch this one on, current will flow this way easily, right? So then you switch this one off, the energy stored in the inductor will be released to the load. So in this way you can actually boost the voltage in here. If you switch on here longer than you switch off, because the amount of energy stored here become very high when you switch off and it release high energy. That's why you can boost the voltage here up to 12 volts, for example. In here the source you only have 5 volts. But the limitation is the internal resistor, because when you switch on here, the energy would be dissipated via the internal resistor, so you can store so much energy on the inductor. Okay, then probably you cannot boost as high as you want in here. So in this problem, you are asked to determine the duty ratio D at which the converter operates, and you neglect all the drops on the semiconductor, which are MOSFET and diode. Okay, you can drop all the voltage drop in here in these two elements. Okay, so what is the duty cycle D? The fraction of the turn on over the total period. Okay, how long? So D taken from 0 to 1. Here you can see here. You program to switch on and off like this, and D is the duty cycle, which means the fraction of the turn on over the period of time. Okay, so what is the value of D? That you can make this boost converter operate where you have voltage source 5 volts and you have load voltage 12 volts. Okay, so what should we do? Like I explained earlier, for buck converter or boost converter, the process to find a relationship between V1 and V2 is to first plot the graph of voltage at the inductor, and then you just use the property of zero average voltage. Then you can find a relationship V1, V2 and duty cycle, right? So in the ideal case of buck and boost converter, you just use one property, and then you can and if you know the duty cycle, then you can easily calculate the voltage and the load. But now you want to design a boost converter where you have voltage of the source here like 5 volt and the load 12 volts. Then you determine the duty cycle D. Okay, so yeah, so like I said, we need to follow the process of drawing the graph of voltage at VL in the case of switch on first. When D is on, so D is on, then the diode here, no, I should call this MOSFET, should be, because this one also this one also D diode, maybe a little bit confusing. Okay, just write full diode off. Okay. This is the MOSFET here. Then you can analyze the circuit only in this loop, right? So what you have from Kirchhoff voltage law, you have V1 because here's plus, here's plus minus, right? So V1 minus you have current here I1 R plus VL equal to 0. So you can have VL equal to
is minus VR or plus?
oh minus, yeah, you're right. So VL equal to V1 minus I1 R, which is 5 minus 0.2 I1. Next, when D is off and diode must be on. Okay. So now what you have, this is here is open, so you have you can analyze the voltage Kirchhoff law, Kirchhoff voltage law in this loop, the big loop. Okay. So KVL again, you have V1 minus I1 R minus VL and minus V2 equal to 0. You have any question up to this point? Okay, good. Then you can find VL equal to V1 minus V2 and minus I1 R equal to V1 is 5 volts, V2 is 12 volts, so you have minus 7 minus I1 R. Oh no, 0.2 I1. Well, so from here we can use the property zero average voltage of VL, right? Need to remember this and this, 5 and minus 7. Okay, so maybe I write here up here. We use the property average VL equal to 0. Then okay, here average VL equal to 0. Then you have when switch on, you have T taken from 0 to dt, right? So the period is dt. So you have dt times 5 minus 0.2 I1 plus Then when you switch off, you take the time taken from dt to t. So you can have the duration is t minus dt. So you get 1 minus d times t. So here you have 1 minus d times t, and all of these times minus 7 minus 0.2 I1 equal to 0, right? Then you do the simplification. Okay, I will write again here. It's better. We are here equal to dt times 5 minus 0.2 I1 plus 1 minus d times t minus 7 minus 0.2 I1, right? And then you can so we can cancel time, and then 5d minus 7d. Oh no, okay, let me, okay, 5d and minus 0.2 di1 plus minus 7 minus 0.2 I1 and plus 7d plus 0.2 di1 equal to 0. 5d plus 7d, so we have 12d, and then minus 0.2 d1. Oh, this one cancel, eh? Minus, and this one plus, so this one cancel, and then 0 or minus 0.2 I1 minus 7 equal to 0. So here you realize that just from one property you cannot solve it, because you have two parameters now, two variables, d and I1. So you need to find another property. You can say property or law or whatever, in order to have another equation which involve at least I1 or d. Then you have two equations, you can solve the problem, right? For the ideal case, you don't have the internal resistor, which is 0.2 here, then you don't have I1, so it's easy to solve, right? In this equation, actually, for the ideal case, you can directly find D, but it's not the case. In real life, you always have internal resistance. Probably it can be small, but it exists. So what is the key idea to get another equation? Okay. It's not easy to think from the bottom up. I mean, if you use the way to like derive the differential equation and solve it, it's gonna be it's not gonna be helpful. So you need to think like top down, think the law that explain, how to say, big picture. Yeah, very important thing. View it in the big picture. So, any of you may have any idea? Any idea, please? Yeah, if you can, you remember my word, but whenever I said big picture, you think about what terms? If you think from the bottom up, you have circuit that has branch, very complicated. You think from bottom up, you need to model, you need to work on each element, each branch, each loop. It's very complicated. But you see something from big picture, just you use some law that cover whatever you have, whatever the brand you have, but it must follow that law. Yeah.
Energy conservation?
Yes, that's good point. That's good. Energy or power, because energy or power. So we use energy conservation or just say power. So the power generated from the input has to be the same as the power as the output plus the power that is wasted. Right? Wasted means dissipated. Yeah, this is huge, big picture, and you don't need to care about the branch of the circuit, right? You just follow that law. So using the power conservation, you have the power generated from the source, and you have power from the load, and plus the power that is dissipated, right? Actually, power P2 is also dissipated, but dissipated at the load that you want. So the formulation just have the same. I mean, these two have the same formulation because both of them dissipated on the resistor, right? On resistors. But anyway, in the resistor, you want variable I and R. For this resistor, you want to use parameter voltage and resistor. Okay. So also P1. Yeah, also P1 you have voltage and current. So the power you have 5 times I1 here. How about P2? P2 here you have voltage and resistor. What is the formulation of power? 12 square over 5. It's V square over R. Correct? Yeah. And this one, you have current and resistor. So it is 0.2 square. No, I square, right? So here is I1 square. Yeah. Actually, from here you can, from this equation, actually you can get I1 first. And so you multiply this, become I1 square minus 25 I1 and plus or minus plus 144 equal to 0. So from here you have I1 1 plus I1 2 equal to 25, and I1, yeah, actually because I already know the solution, I1 1 times I1 2 equal to 144. So actually I1 1 equal to 16 and I1 2 equal to 9. So these two plus equal to 25, and it multiply 64 for here 60 no 9 plus 6 54, you get 4 here 50 5 9 plus 5 14, correct, right? Okay, so you have two solutions for I1. Then you substitute I1 to this equation, just call it equation number 1. Okay, for I1 equal to 16, then D equal to 7 plus 0.2 I1 over 12 equal to 7 plus 0.2 times 16 over 12. So you have one value here. Sela, can you calculate it? 0.85. And then for I1 equal to 9, then D equal to 7 plus 0.2 I1 over 12 equal to so Sila
0.33. Oh, 73.
73, maybe all three, yeah? Because 12, yeah, 12 in denominator, you have 3 in denominator, so maybe it's not, yeah. Okay, so it means if you have internal resistor, you can control to get the load two-way, whether you use duty cycle with this value or this value. But then let's try to analyze a bit more using which one is more energy saving, because for sure that for these two cases you can have your boost converter operate as you want. I mean, the output voltage is 12 volts. But let's think a little bit more in terms of power. Of course, we always want to save power, save energy. So which case should we choose? Thomas, can you? Which case should we choose? The 0.85 or 0.73? Alex? Which case? I think Lucas may know, but I don't want to ask him. No? Yeah, for sure, any case, your boost converter will operate normally. Just, sometimes we want to save a little bit, save power a little bit.
So it's the second one.
Why?
Because we bring the value of I to substitute in the equation of D. So, and D is related to the voltage, the VF. So
Same formulation, right? Just same formulation. Because I use the term sell power a little bit. So look at the power of the source. The power of the source here, you want to sell, it means the power of the source should be small. You use the smaller one. So how it's Which case the power is smaller? Yes, R equal to 9. And if you look at in terms of power, almost twice, right? For this case, almost twice of this one, right? Yeah, so in this case, we choose this case, right? Yeah, power or energy, you can say. So in real life, when you work on boost converter, you see there's some strange behavior. Why strange behavior? In the ideal case, if we look at the ideal case, if compared to the ideal case, we have V2 equal to 1 over 1 minus D times V1, right? And 1 over 1 minus D, always greater than 1. Okay? Always greater than 1. So from this relationship, we say, well, as long as I use D close to 1, so I get the denominator close to 0, which means I have this ratio close to infinity. So it's like if you increase the duty ratio from 0.73 to 0.85, you got higher voltage of the output, right? It looks like that. If you assume that your boost converter is ideal, there's no internal resistance in the input, so you try to increase D, increase, and then you expect that the output voltage increase as well. But then it's not the case, and you realize that at some point, no matter how much you increase D, the voltage of the output of the load cannot increase anymore. See? Then, of course, your boost converter is not ideal. You need to analyze using this way, right? Yeah. I said you analyze using this way. I mean, if you want to change the variable or the parameter D and you want to observe V2, then you don't use V2 as variable. Let's say V2 as variables, okay? And then you formulate it as a function, right? You have I1 there and you have D there, but using power conservation, you can substitute it, and then you get the V2 as a nonlinear function. Actually, it a function of like degree 2, like polynomial degree 2, and then you can observe the behavior using that function. Okay. Any question? Yeah, so here I want to say, compared to the ideal case, D is a unique solution here. No, I'm not D. D is how to say? D is unique, right? D is unique. D is unique, yeah. To have the converter operate. Okay, so this problem is finished. Let's take a break, 10 minutes.